Bonjour Lucille, bonjour à toutes et tous.
Bonjour.
Donc on va démarrer ce séminaire à l'heure prévue. On a quatre présentations. La première de l'équipe Sumo, Lucille va nous parler de dingue. Je vous rappelle que l'idée est de couper vos micros et de poser vos questions sur le chat pour la discussion qui aura lieu à l'issue de cette première présentation. Et je remercie Lucille d'ouvrir le bal, si je puis dire, par cette présentation. Donc tu peux partager ton écran. Le séminaire est enregistré, vous pourrez aussi le retrouver sur le site de la faculté.
Okay, thank you. 1 minute. There we go.
On
All
voit,
right.
voilà, c'est parfait.
C'est bon.
Ouais.
Alors moi, je ferme juste ça. Ok, parfait. Euh, 1 minute. Okay, so I'll speak in English so that everyone can follow. And my name is Lucille Kalman, and I'm a postdoctoral researcher, and I'm happy to share with you some recent results on this study on dengue knowledge, attitudes, and preventative practices in the French and Italian general population. Um, so Okay, so dengue fever is a mosquito-borne disease transmitted by the Aedes mosquito through bites of infected mosquitoes, and it's been historically endemic in tropical and subtropical regions, where it causes an estimated from 100 to about 400 million infections worldwide per year. And these infections are asymptomatic or can cause flu-like symptoms in mild cases, and these symptoms last between 2 and 7 days. But in more severe cases, it can lead to hospitalization and death. So there is no medical cure, just symptom management. At the moment, there are two licensed vaccines on the market, I think worldwide, if I'm not wrong. But these are not recommended in France or Italy, or I think more broadly in Europe for the general population. So mitigation strategies to mitigate the spread of dengue or limit outbreaks rely on the limitation of mosquito proliferation and the limitation of feeding opportunities on human hosts. So in Europe, the Aedes vector has been increasingly colonizing the territory. I think at the moment it's present in France, in nearly all departments, if not all of them. And there has been local outbreaks of dengue, increasingly recorded, more and more often, especially in the summer since 2010, in France, Italy, Spain, especially. So, in this context, we designed a questionnaire to assess the knowledge, attitudes, and preventative practices related to dengue in Europe, especially in France and Italy. And we leveraged participatory surveillance cohorts in France, which is the GripNet cohort, and in Italy, the InfluEP cohort. And these are cohorts of the InfluenzaNet European network, which are participatory cohort used for the surveillance of respiratory viruses. So in France, we sent out this survey in a single wave at the end of July 2024, and we included responses filled in between 29th of July, which was when the survey was initially sent out, and the 6th of August. And in Italy, the survey was sent out multiple times to the cohort participants between May and October. And for the study, we included only the first response of each participant. So each participant was associated one response, which was the first one that they sent out to the questionnaire. And overall, we included 2,904 responses, with the majority in France and a minority of 404 responses in Italy. So I won't go through all the questions in details, but to give you an overview of the questionnaire, this was covering dimensions related to knowledge with the awareness of dengue as a disease, the knowledge of different characteristics of dengue, the personal appreciation of the participants' knowledge of dengue. We also asked about participants' symptoms and travel history, if they had symptoms, about their information-seeking behaviors, their fears related to dengue and why they feared each consequence of dengue. Um, we also asked about their vaccination status, whether they would be willing to be vaccinated and why not. And finally, we asked the participants to rate preventative measures and which preventative measures they adopted. And we also asked them about whether they had dengue in the past, whether they knew of someone diagnosed with dengue in their among their acquaintances. So from the intake profile of the participants, we also knew the age, sex, the education level, whether they had comorbidities, the occupation, the zip code of residence from which we could infer whether they resided in a rural or an urban commune, as well as whether they resided in a department or a province for Italy where a local transmission of dengue had been detected, reported in the year prior to the study. And this is a profile that, an intake profile that all participants had to fill in, not specifically for our study, but in general to join the platform. So our analysis aimed to identify the statistical determinants of awareness of dengue and of knowledge of the different characteristics of dengue, as well as the adoption of preventative measures and the willingness to be vaccinated, as well as the reasons for refusal. So we adjusted our two samples in Italy and France on age, sex, and education level using post-stratification weights. So typically, and this is often the case with these cohorts, the samples are biased towards older respondents and respondents with a higher education level. And for the statistical analysis, we modeled binary variables such as, have you heard of dengue? Yes or no, with multivariate logistic regression, which we adjusted with the post-stratification weights. And for ordinal variables, like how many characteristics of dengue are known by the participant, instead we used multivariate ordinal regression. And we obtained final models using a backward stepwise variable selection, where we first tested each determinant through a univariate analysis, eliminating those with a p-value larger than 0.2. And from the determinants that met this first step, we then constructed the multivariate model from which we eliminated iteratively the determinants with the highest p-value until we had a model where all determinants had a level with a p-value below 0.05, so considered to be statistically significant. And we conducted this analysis on a merged dataset that included both French and Italian respondents. So the first thing we asked the participant was, are you aware of the existence of an infectious disease called dengue in your country or around the world? And we were relieved to see that 91% of the participants answered yes to this. This is adjusted with respect to sex, education, and age. And then when we looked at the statistical determinants of awareness of dengue as a disease, we found that being male, university educated, living in a urban, commune, having a history of 2 or more dengue symptoms, and residing in France was associated to being aware of dengue. So to those participants that had answered yes to whether they knew of dengue as a disease, we then asked them whether they were aware of each of these characteristics of the dengue disease. These covered the transmission mode, the clinical manifestation of the disease, the treatment option or management of the disease, and the risk factors, especially the fact that if they had had dengue in the past, they were more at risk of having severe symptoms. And we found that 94% of the participants in both samples knew that dengue is transmitted through the bites of infected Aedes mosquitoes, and 88% knew that severe cases of dengue can lead to hospitalization and death. But when we looked at the other characteristics, we found that actually only 41% of the participants knew that dengue can be asymptomatic, and more worryingly, 26% knew that if you had already had dengue in the past, you were more at risk of developing severe symptoms. So these two characteristics were the least well known. So, to investigate the determinants of the knowledge of the characteristics of dengue, what we did is that we considered as outcome the number of known characteristics out of those eight. Again, for the participants that knew that dengue exists, and we binned this number for each participant in four categories from poor, medium, good, and excellent knowledge, where participants knew the vast majority of the characteristics. And we modeled this outcome with an ordinal regression. So these are the determinants that we obtained in the final model. I didn't specify it before, but those that don't have an odd ratio specify that those variables that were excluded in the backward stepwise regression, yes, variable selection. And so here for the number of known characteristics, we found that being vaccinated, having sought information specific to dengue, and having a higher concern level about dengue was associated with knowing a larger number of characteristics. And instead, having comorbidities, being in the age bracket 20 to 44 years old, or living in a rural commune was associated with decreased knowledge of dengue, so knowing fewer characteristics. We also asked the participants how effective they thought each of these following measures were at reducing the risk of getting dengue. So the measures were those that are typically recommended for um, protecting oneself against dengue, and they covered covering arms and legs with long-sleeved clothing, using repellent, avoiding swampy areas or areas with high density of mosquitoes, avoiding traveling to at-risk areas, installing mosquito nets, and removing stagnant waters from balcony and so on. And each participant rated each measure from 0, which is not effective at all, to 4, which is highly effective. And these are the efficacy rating that the participants gave for each measure. And what we find is that all measures are rated as quite very or extremely effective by the vast majority of the participants, so that they perceive that as working. And over 80% of the respondents for each measure rate them as at least quite effective. So those are quite high rating. So we next asked the participants if they adopted the following behaviors to reduce the chance of contracting dengue, and these were the same set of measures. And what we found is that removing stagnant water was the most adopted measure by 44% of the participants, and 33% of the participants also reported avoiding swampy areas or areas with high mosquito density, but instead wearing long-sleeved clothing, not locked-sleeved clothing, and installing mosquito nets were the least adopted by the participants. For installing mosquito nets, it makes sense because these may not be always applicable or possible to install for the participants. And overall, 56% of the participants adopted at least one of these measures, which is quite high. So to investigate the determinants of the adoption of preventative measures, we looked at as an outcome the total number of preventative measures that were adopted by the participants. And we bin this number in four categories from 0, which were the participants that adopted no measure at all the way to 5 and 6, which are the participants that adopt 5 or 6 of these measures. And we model this outcome again with an ordinal regression, like the knowledge of characteristics in our analysis. And so these were the determinants that we identified in our final model. And we found that being female, vaccinated, having comorbidities, being concerned, having sought information regarding dengue, and perceiving a higher efficacy to the measures, as well as being 45 to 64 years old, was associated with adopting a larger number of measures. And instead, having a worse knowledge of dengue, so knowing fewer characteristics, or being employed were associated with adopting fewer measures, a smaller number of measures. So we also asked participants if they would get vaccinated for dengue if they were offered a vaccine, and 59% of the participants would be willing to be vaccinated in our sample. This was asked to the participants that didn't receive a vaccine, that were not vaccinated, and this was the vast majority of our participants, since only 11 of them had received a vaccine for dengue. And the factors associated with being willing to be vaccinated were residing in Italy, being in the younger age bracket, being more worried about dengue, so reporting a higher worry level, having sought information related to dengue. Um, and instead, the factors associated with refusing to be vaccinated were being female, having a lower education level, living in a rural commune, having a rural domicile, being employed, knowing of a case among one's contact, and having a good knowledge compared to an excellent knowledge of the characteristics of dengue. So here, some of these factors, like knowing of a case, are not so intuitive, but we think that this is because the vaccination attitudes are not always shaped by rational factors. So for those 44% that of participants that refused to be vaccinated, we also asked them why they wouldn't be vaccinated against dengue. And we offered the following set of options, and we also participants could also reply in their own words why they didn't want to become vaccinated. And the two reasons that were the most commonly cited were perceived risk, which was offered as I don't think I'll get dengue, and this was given by 37.4% of the participants. And I don't belong to any risk groups, which is a marker for perceived susceptibility, which was cited instead by 37% of the participants. And those are again the participants that would not be willing to be vaccinated. So we looked at the determinants of these of the two reasons that were the most often cited. Instead, the other reasons were related to vaccine safety or vaccine effectiveness, and more broadly perspective related to vaccination. And so for those two reasons, I don't belong to any risk groups, and I don't think I will get dengue. These are the final determinants that we obtained with our logistic regression model. And what we find is that the having a higher worry level was associated with a lower likelihood of citing those two reasons, but instead the rest of the determinants were quite different between the for each reason. So we found that residing in Italy, being employed, having a good compared to excellent knowledge was positively associated with refusing for no perceived susceptibility. Instead, living in Italy was negatively associated with the I don't think I will get dengue reason. And similarly, being employed was positively associated with the I don't belong to any risk group, but negatively associated with I don't think I'll get dengue. And then, so factors negatively associated with refusal for no perceived susceptibility was being younger, having a lower education level, being worried, and having comorbidities. And instead, we had more likelihood to refuse vaccine due to no perceived risk for participants that had a symptoms history or lived in a rural domicile, and participants instead that resided in Italy, were employed, had sought information, were worried, or had a higher perceived knowledge, were less likely to cite this reason. I don't think I'll get dengue as a reason for vaccination refusal. So to conclude, our analysis found that there is quite a high awareness of dengue in both Italy and France, with 91% of the participants that had heard of this disease. And there was a high knowledge of some of the characteristics, like its transmission mode, which was known by 94% of the participants who had heard of dengue. But instead, the fact that dengue can be asymptomatic, and especially the increased risk associated with reinfection, was known by very few participants, with just about one quarter of the participants who had heard of dengue knowing about this last characteristic. Preventative measures against dengue that we inquired about were perceived with quite a high efficacy by the vast majority of the participants, and at least one of these measures was adopted by about 56% of the participants. And we saw also quite a high vaccination willingness, with 59% of participants being willing to be vaccinated. And refusal of vaccination was most often linked to low risk perception or low risk susceptibility, low susceptibility perception. Sorry. Having sought information related to dengue and having higher concern levels were found to especially shape knowledge of dengue and adoption of, so this is knowledge of the characteristics of dengue, adoption of more preventative measures, and willingness to vaccinate. And instead, not instead, but and moreover, the knowledge of the characteristics of dengue itself shaped the adoption of preventative measures together with higher perceived efficacy of the measures at the local epidemiological context through the presence of an autochthonous case, which I didn't highlight in my slides before. The occupation of the participants, the gender or the sex of the participants that they reported, the vaccination, and the symptom history. So this shows that so what we find is that targeted communication strategies that account for these factors then are important in order to enhance preparedness and outbreak prevention, to then raise the knowledge and encourage the participants to adopt more preventative measures and protect themselves. So I'd like to thank Victoria, Marion Debin, Romain Marmora, Clément Tobelin at IPLESP who are participated to this study, and our collaborators at Aix-Marseille University and ISI and Queen Mary that also participated to this study. This was funded by ANR and two EU Horizon projects. And I'm happy to take some questions.
Thank you, Lucille, for this presentation. A lot of different findings. There is one question, only one at the moment, by Pierre-Yves. When you said vaccinated in the risk factors for knowledge, preventive measures, what kind of vaccination was it?
Yeah, I'm afraid you can't see my slide anymore. But this was vaccination against dengue. So this was yeah,
The type of vaccine was specified because you know there are maybe some different type of vaccination for dengue, and we know that if the serotypes included in some vaccine can increase the risk of severe dengue in case of infection if you have been vaccinated with another serotype than the circulating serotype. So, was it specified?
no, we didn't specify this. We just asked them if they had received a vaccination against dengue in the past.
Okay.
Yeah.
So we are waiting some other
Yeah, I
question.
can see another question from Pierre. Do we know whether the characteristics do we know whether the characteristics associated with adopting preventive measures is the same as for
For
example,
COVID.
COVID-19. Um, so Jen, let me share the slides again. I left the full screen mode and lost them. Um, Now we should be able to see this. So preventative measures. Yeah, so gender, for example, and is a common determinant of adoption of preventative measures for COVID-19 as well. And here, this is something that we found again. For the other one, I'm not sure. I think that having higher concern was also shown to be a factor of adoption of measures during COVID-19. So here the concerns were related to dengue, but for COVID-19, related to COVID-19. Yes.
Okay. So there is a question from Raphael. in the introduction, you mentioned cases of dengue since 2010. Do you
Mm.
mean local transmission of dengue in Europe?
Yes. Yeah, so I mean, yes, I mean local transmission of dengue because, of course, before this, there had been introduction through traveling individuals, but these refer to outbreaks where there is transmission on the European soil, which doesn't include the French overseas territory. So where individuals had no link with no travel history. Um, and were had been determined to have been infected with the disease in Europe. Yes.
Thank you. I have a question, several questions indeed. Uh, can you comment about the representativeness of your sample as the source population, with regard to the source population as respondents were selected from social networks specialized in infectious disease? So what about the representativity with regard to the source population?
Yes, so okay, so here so this is specific to the French participants, but this is the we can see the distribution of the age of the respondents, the gender and the education. And so these are the three dimensions where we could adjust with the post-stratification
Okay,
weights.
okay.
But it's true that I mean, these participatory cohorts, the participants in these participatory cohorts are typically quite engaged with the cohort, so they have this may affect their responses. For example, when it comes to vaccination willingness, they may be more willing to be vaccinated than the general population, let's say, are um, because they have this démarche of
Okay, to participate to
volunteering.
this. Okay.
Exactly. So, and this is something that we are not able to take into account, and we have to remember, of course.
And my other question was related to the analysis you performed. Was there a place, a room for a kind of structural modeling equation? Because there are several outcomes that seems related to each other, and if you
Mm.
are more willing to be vaccinated, you also maybe are more compliant to preventive measures and aware about or worry about dengue. So, is there a place to do some kind of structural modeling equation?
So this is not something I'm familiar with, and so this is not something that we did. But what we did do was to test out some interactions, possible interactions between the determinants in the model. So to if we check one of them, so we looked as well at including interaction terms in the regression analysis. For example, between let's say vaccination status and having search information and so on. And this is something we tested for the in the as a supplementary analysis, and that we include in the paper. But no, in terms of structural equation modeling, this is not something we did.
Thank you. Thank you very much, Lucille. There is no more question on the chat, so I think we can move to the next presentation, which is given by Devin Parker from the ESMA team. So, Devin, the floor is yours. You can start when you want.
Excellent. Thank you. I'm going to share my screen.
So,
Was
yes, it's good. It's
okay,
okay.
great. Okay. Hello, everyone. I'm a postdoctoral researcher with the ESMA team. Today I'll be sharing some preliminary results from a project I've been working on with ESMA that focuses on how the built environment impacts children's health. Vast amounts of literature confirm that the environment is a key determinant of health, behavior, development, and social inequalities. Over time, studies have shown to consider not only individual characteristics, but also characteristics of groups or contexts to which individuals belong to better understand the prevalence and distribution of health and disease. Neighborhoods, or residential areas more broadly, have emerged as relevant contexts because they possess both physical and social attributes which could plausibly affect the health of individuals. In the US and in Europe, the analytical intersection of neighborhoods and health have been both exceptionally broad, regionally, or specifically defined, like cities, not using specific addresses or access points. And to this point, the progress in spatial analysis techniques and data granularity now allow us to study neighborhoods in a much more detailed and sophisticated manner, which has not been possible previously. In this study, the built environment is defined as neighborhood walkability. Walkability refers to how friendly or amenable an area is to walking. More walkable neighborhoods are associated with higher residential density, presence of pedestrian pathways, and diversity of destinations or resources. Walkable neighborhoods have been shown to increase social cohesion, increase physical activity, lower blood pressure, and improve memory. Walking as a primary mode of transportation has proven both environmentally friendly and beneficial for residents' physical and mental health. In addition, walkable neighborhoods are associated with reducing greenhouse gas emissions. In terms of children's mental health, it has been reported that nearly 1 in 6 children in Europe has a developmental delay from 3 to 10 years old. Most research on children's mental health and development have focused on the socioeconomic and social position of families, neglecting to account for the complex role of the environment in which they live. However, emerging evidence has shown that access to green spaces are associated with higher cognitive function and fewer peer relationship problems. Studies that have examined walkability and health outcomes have largely focused on physical activity and obesity in adults. Therefore, understanding neighborhood composition and children's mental health has remained unexplored until now. I'm presenting here a conceptual diagram that depicts the complex relationship between contextual factors, neighborhood factors, and health. The socioeconomic position relates to resource inequalities, which is also associated with neighborhood environmental factors and in social environments, which then contribute to behavior and stress, and finally, their health. Underlying all of this are obvious personal characteristics, both biologic and material. So the purpose of this project was to study one aspect of the built environment, neighborhood walkability, and its association with children's mental health. This study uses data from the ELF birth cohort study, established in 2011. ELF recruited just over 18,000 newborns from across France. This is representative of 1 in 50 births. This is a longitudinal, nationally representative cohort. It includes diverse qualitative and quantitative data, as well as geographical locations for all ELF participants. The current study uses data from the 5.5-year-old wave. All addresses were geocoded. So to calculate walkability, we use the ELF geocoded addresses, and then I calculated the 500-meter walkable buffers or spatial areas from the addresses. Walkability scores are a composite measure of 3 different publicly available data sets in France. Residential density was from INSEE at the iris level. Street connectivity was defined by intersection counts provided by road network data from Bere Topo. And land use mix or amenities or resources were defined by BPE. Land use mix is an entropy score that is based on four categories of resources. Places defined as leisure, office, residential, or sorry, institutional, and retail. Finally, each of the three parameters were standardized and converted into z-scores for each residential buffer and then summed for a final score. The example I present here shows the different types of resources available for someone living. You can see this is where they live, and within 500 meters from their house, these are the number of different amenities or resources available to them. The primary outcome was mental health based on SDQ scores from children in the ELF cohort. These subscales were defined as symptoms of emotional problems, conduct problems, hyperactivity, and peer relationship problems. Each scale includes 5 questions. Based on these scores, each subscale then includes categories of normal, borderline, or abnormal. The SDQ at 5.5 years has been previously validated in France. Covariates used in the statistical analysis were selected a priori as indicators of mental health distress. Characteristics of the children include age, sex, prematurity, number of siblings, and a child's place of residency, which is defined as living with both parents, one parent only, or an alternative arrangement. Parental characteristics include education level, income, employment status, smoking use, alcohol use, parental depression, and parents' migratory status. We also included urban or rural residency. We used multiple imputation to account for missingness. We used cohort weights to account for population sampling. And the walkability exposure was defined by tercile. And then finally, we used multinomial logistic regression for each of the SDQ subscales. Our cohort started with just over 10,500 children. We applied exclusion criteria, including whether they were if they were twin burrs, those with profound hearing impairment, and those living in a foster home. We also excluded any of those with missing outcome data, and our final cohort is just over 10,000. A general description of our cohort. Most children lived with both parents. Of the children in the cohort, most had one other sibling. Both mother and father education level was high. Most children in the cohort lived in a home that was above the median. Both parents were working. Mother was French. No psychological difficulties from the mother. Neither parent was at risk of depression, and most of the children lived in an urban area. And all of these characteristics you can see are statistically significant by walkability tercile. I wanted to point out this Paris case study that I did just to sort of highlight walkability and how it changes based on the 3 different components. Like Paris is a very walkable city, but you see that the shades and the yellow and orange shades are the least walkable in Paris, and the most walkable are on the perimeter. And this is possibly due to a result of the land use mix and population density. Like here, there may be just more, less of a diverse amount of resources available, like more cafes, where there are other things like parks and playgrounds and other amenities available here. Um, so by the bivariate analysis for walkability, terciles and SDQ, none of the subscales were significant. So there's just in this simple analysis, there is no association between subscales and walkability, but of those with abnormal symptoms, most had conduct problems. However, after adjustment, we discovered some interesting findings. In the upper left, we see that those with hyperactivity and inattention symptoms had a 12% reduced odds of symptoms of with in the highest walkability tercile. Um, in the lower left, there is essentially no association with symptoms of conduct difficulties and neighborhood walkability at any level. In the upper right, we see that those that had exhibited emotional difficulties had a slightly increased risk of emotional difficulties in the moderate walkability tercile, but that went away with the highest walkability tercile. And finally, we found we found decreased peer relationship problems in the highest walkability tercile, um, approximately a 20% lower odds of peer relationship problems. So this is the first study to calculate walkability for all of France. And secondly, it determines the association between neighborhood walkability and children's mental health. We found that increased walkability is associated with fewer symptoms of attention hyperactivity and inattention. And similarly, we found that increased walkability is associated with fewer symptoms of peer relationship problems. We did not find a significant association with emotional difficulties and conduct problems. So we can conclude that neighborhood walkability is related to levels of psychological difficulties, but this is these are preliminary results and warrant further research into this complex relationship. So in the vast amounts of literature available on looking at the built environment and mental health, it's pretty mixed. A study found that the built environment and one recent study found that the built environment and depression were positively correlated, and they were using the use of antidepressants as their indicator. And then another study found that neighborhood walkability is actually protective of of depressive symptoms, and they were using a questionnaire similar to SDQ. So these projects, these studies that define the literature are mostly based in adults and typically older adults. Walkable neighborhoods may actually correlate with higher air and noise pollution, which could contribute to depressive symptoms. However, a component of walkability, population density, may also increase social interactions that may decrease depression. Studies have shown that neighborhoods with higher walkability tend to have lower traffic volumes and speed limits, which may contribute to safer pedestrian environments for children. This study has several strengths. First, this study is using nationally representative data from the ELF cohort. This data includes detailed information on health outcomes and parental characteristics. This data is also merged with precise geographic data. SDQ has been previously validated in France. And finally, this study is multidisciplinary using quantitative and qualitative and spatial data. And this combination of very rich data from the ELF cohort and spatial data, I believe, has several applications within and outside of academia. And with such a complex study, there are several limitations. At 5 years old, the SDQ was provided by parents and did not include the SDQ reported by school teachers, which is done at 4 years old. Um, Critically, the walkability scores do not measure if the children or children and their caregivers actually walked and where to. Um, it's implied, but we don't know if they where they actually walked to or how often. Um, it's a composite measure of the propensity to encourage walking. And physical activity and after school activities that are associated with hyperactivity and peer relationship problems were not included. And this study does not include other environmental factors, including perceived neighborhood quality or other factors like access to green spaces, density of air pollution, or intensity of heat. We found that in our cohort examined children's mental health, neighborhood walkability, and neighborhood walkability was largely driven by access and diversity of resources. These may include access to parks, playgrounds, and schools, places that can positively contribute to children's health. And we cannot directly determine this, but walkability and physical activity may explain lower rates of hyperactivity. Walkability and neighborhood social cohesion may also explain lower peer relationship problems. Walkability is a metric to characterize neighborhood composition, a very diverse and complex concept. A seminal report from the UK called Cities Alive argues that evaluating how children interact in their environment, specifically walkability and their health outcomes, is important to identify places where improvements can be made. Walkability is not only associated with health, but other aspects of the environment, including neighborhood safety, community, environmental sustainability, access to nature, and resilience, like climate resilience, response to threats, and multifunctionality. This preliminary work supports several directions in future work. First, the network buffers that were used were at 500 meters, and this is roughly equivalent to a 5-minute walk. It would be useful to evaluate the same methodology at spatial distances at 800 meters or 1200 meters, which is equivalent to 10 minutes or 15 minutes walk. It would be beneficial to evaluate this relationship between neighborhood walkability and children's health longitudinally, specifically to see how these patterns change between 5 and 10 years. Studies have shown that walkability is associated with lower green space, more concentrated air pollution, and higher heat concentrations like urban heat islands. These contextual factors should be evaluated in relationship to neighborhood walkability and children's health. Access to physically active spaces, specifically parks and playgrounds, are of equal interest in the concept of neighborhood walkability and children's health. And while this study presents aspects of children's mental health, the assessment of children's psychomotor development and their lived environment is equally important. And that's all. Thank you very much for your attention. I'll be happy to answer any questions.
Thank you, Devin, for this nice presentation. There are several questions on the
Okay.
chat, and I think you already did reply to the first one, which was from Muriel Marie-Croze about 500 meters
Oh, okay.
threshold.
Yes, but thanks, Devin, for this nice presentation. But I think that you answered to my question because I found some 500 meters very far from the
No.
residence. I don't understand why you use this distance.
It was
rational.
Yeah, it was based on the literature mostly. But this is a preliminary.
Yes, sure.
Preliminary. So,
Sure, no problem.
so I started with 500 meters just to kind of go through the motions of calculating walkability because it includes so many data sets and it's a process. And so I just started there, but in the process of doing that, I realized that 500 meters is not very far.
Yeah, sure. Okay.
So those are my next steps.
Okay. So there are three questions from Giovanna Francello from
Okay.
this team. Can you look at the question or
Mhm.
do you want me to read it?
Oh, I can.
So about the definition of
Mm-hmm.
in children versus adults.
Yeah, that's a good question because you know, in the literature, this is what we have. Um, and I think that that's definitely something to consider. Like, um, are these children actually like if we're calculating land use mix, then we're including things like banks, boulangeries, cafes, you know, IKEA. It's like, are these children actually is this are they actually going to these places or not? So that's definitely something to consider. And um, which is why in the future work that I want to do, I want to scale that back and look at places that would are more relevant to where children would actually go. Um, and again, like this is just a starting point using the literature that exists and has been defining walkability. Um, and and the neighborhood walkability was defined by someone from Canada and has been often used to define spaces in the US. And the structure of European and French cities is very, very different.
Okay, so I think you also replied to the comment by Pierre-Yves about cafes in the amenities, which are not very well adapted for children.
Right, yeah. Cafes, yep. Yeah, so again, this is just a starting point, and in that process, we can kind of um, tailor it much more much more for the actual population of interest.
And there was also a question from Pierre Chauvin. Do you plan to focus your analysis on Greater Paris?
Well, the aim was to look at all of France, and so I presented that as an example of how varied it can be. If we're, the example of Paris, like it's objectively very walkable, but how the walkability scores are kind of weighed more based on the three components that define it. Um, it's something to consider, just Greater Paris, but the goal was to look at all of France and to include more of the social spatial inequalities in future work.
Okay.
Education level, yes. I found a direct correlation between income and the FDEP score. And so that's another thing that I want to explore further because neighborhood deprivation and walkability and health in general is positively correlated with the deprivation level, as in um, like and health. So yeah, that's something that we want to explore further.
Thank you. Any other question? I had a small question about the paper published in 2010 about
Mhm.
walkability.
Yeah.
Can you tell us how it was validated, this score?
Yeah, so the paper from Frank in 2010, yeah. Yeah, so he he developed the walkability score, and then there's actually a company that's called Walk Score that does something similar. Um and so they compared the results between this proprietary company and Frank's Walk Score, and they were um that's how it was validated.
Okay, thank you. And the final question by Pierre-Yves, I guess he knows the response. The response. Is it Paris on the picture?
I don't know actually.
I guess not.
Okay. I'm very interested to know where it is though.
Okay, thank you very much.
Okay, thank you.
Thank you. And we move to the next presentation by Klepi Virtin. Hello, Francisco. So you can start when you want.
Okay, sorry. Are you able to see?
Not in full screen for now.
Tac.
Okay, that's fine.
And now you can see. Well, I'm going to present in French though. Euh, donc, bonjour à tous. Je m'appelle Francisco. Je suis interne de santé publique dans le service de santé publique de Saint-Antoine. Et je vais vous présenter le travail que j'ai réalisé ces derniers mois dans le cadre du M2 qui a été encadré par Benjamin Clément, qui est CCA ici dans le service. Et donc le projet, il s'intitule TAP-FN for Causal Inference, Narrow Confidence Intervals, but Poor Coverage in a Simulation Study. On va commencer par faire une petite introduction euh, avec l'estimation d'effets de traitement à partir des données observationnelles. Ensuite, on va discuter l'intérêt d'utiliser le machine learning pour faire ce type d'estimation. Et on va finir avec l'utilisation de TAP-PFN les résultats de notre étude. Donc, dans ce diapo, on peut voir deux graphes causaux. On voit X qui représente le traitement, Y qui représente l'outcome et Z qui représente des variables pronostiques. Et on voit ici dans le graphe à gauche, le graphe qu'on tombe souvent à partir des données observationnelles, c'est-à-dire que les facteurs pronostiques, ils vont être à la fois des causes de traitement et causes de l'outcome, c'est-à-dire qu'on va les interpréter comme des facteurs de confusion. Et donc, pour estimer ou identifier d'abord l'effet causal de X sur Y, il faut qu'on s'en passe d'au moins une de ces flèches sortant de Z vers soit le traitement, soit l'outcome. C'est notamment le cas à droite lorsqu'on a des données interventionnelles à partir des essais randomisés puisque la variable x, donc le traitement, il dépend uniquement de la randomisation et donc il n'est pas influencé par les facteurs pronostiques. Et donc l'identification de l'effet causal d'x sur y, il va être plus simple puisque on va pouvoir interpréter l'association entre ces deux variables comme un effet causal. Euh, donc, pour faire le pas, comment s'en sortir avec des données observationnelles, on peut essayer d'avoir un essai dit conditionnellement randomisé en respectant certaines hypothèses. Ces hypothèses s'appellent des hypothèses d'identifiabilité où on a la positivité. Donc, c'est-à-dire qu'il faut que chaque bras de traitement, enfin, que tous les individus inclus dans notre étude soient capables d'être affectés dans les deux bras de traitement. Autrement dit, on ne peut pas avoir des individus qui ont des contre-indications à être traités ou ne pas être traités. C'est notamment le cas quand on a des médicaments à évaluer et on a des patients qui ont des allergies à ce médicament et donc ils seront toujours non traités. Donc il faut qu'on respecte la positivité, soit en enlevant, on peut enlever ces patients de notre étude. On a donc l'autre hypothèse aussi centrale, c'est l'échangeabilité conditionnelle. Ça veut dire que les facteurs qu'on a identifiés comme étant confondants, ils ont été tous identifiés et donc on va pouvoir les prendre en compte dans notre analyse et en les prenant en compte, on va faire en sorte que les groupes entre ceux qui ont été traités et ceux qui n'ont pas été traités vont devenir comparables au sein de chaque strate de Z, donc pour les mêmes caractéristiques des patients. On a aussi une autre hypothèse qu'on appelle donc une hypothèse statistique qui est la spécification correcte de modèle qu'on va utiliser. Donc, pour rentrer doucement, je vous ai pris un exemple des points donnés d'une fonction définie comme x puissance 2. Et si, par exemple, on essaie de modéliser ces points avec une régression linéaire, on trouvera qu'aucune droite sera capable de bien modéliser, bien fitter ces données, puisqu'elle n'est pas adaptée. Et donc, c'est l'exemple d'une mauvaise spécification. Donc, pourquoi c'est important? Parce qu'on va modéliser dans cette approche d'estimation d'effet de traitement, soit l'outcome à partir d'une G-computation, soit le traitement avec l'IPTW, donc la pondération par l'inverse de la probabilité de recevoir le traitement, soit avec des méthodes doublement robustes comme l'IPTW ou le TMLE. Donc ces méthodes, elles sont appelées doublement robustes puisqu'il suffit que seulement une de ces méthodes précédentes soit bien spécifiée. Mais si aucune de ces méthodes est bien spécifiée, alors la méthode doublement robuste ne sera pas bien spécifiée non plus. Et donc, pour voir un peu, suivre un peu la G-computation et l'IPTW, donc ici à gauche, pour suivre les étapes, on va commencer par modéliser l'outcome en fonction du traitement et des covariables Z. Et ensuite, on va utiliser ce modèle pour prédire l'outcome pour tous les individus en forçant d'abord tous les individus à être x égale 0 et ensuite on va forcer tous les individus étant x égale à 1 et on va comparer donc les résultats obtenus, donc les prédictions. Du côté de l'IPTW, on va plutôt modéliser le traitement et donc en fonction des caractéristiques des patients, donc des facteurs qu'on a identifiés, et on va prédire la probabilité de recevoir le traitement en fonction de ces caractéristiques, et on va utiliser ces prédictions pour avoir des poids pour chaque patient qui seront pris en compte dans la comparaison de la probabilité de l'outcome entre les deux traitements. Donc, en gros, ce qui est en rouge, enfin, ça va être un choix méthodologique supplémentaire, c'est-à-dire qu'on peut choisir le modèle le mieux adapté pour arriver à avoir une bonne spécification de nos modèles soit selon la nature des variables, soit par rapport à nos données, et donc pour essayer d'avoir un modèle bien spécifié. Et c'est pour ça qu'on parle souvent de l'intérêt du machine learning pour appliquer ces méthodes puisqu'il serait capable de capturer avec plus de flexibilité des relations qui peuvent être non linéaires entre les variables, avec des interactions complexes entre ces variables dans le modèle, et aussi avec l'avantage de ne pas avoir besoin d'une spécification avec une formule lors de l'utilisation de ces modèles. Néanmoins, pour arriver à faire une bonne utilisation de ces méthodes machine learning, on a souvent besoin de passer par des optimisations de ces hyperparamètres, ce qui s'achève normalement avec une méthode robuste par validation croisée. Et on a également aussi souvent besoin d'une mesure d'incertitude pour nos résultats, donc des intervalles de confiance qui s'obtiennent le plus souvent aussi avec un bootstrap. Et donc la combinaison de ces deux étapes peut devenir assez contraignante dans la vie réelle. Et donc c'est pour ça qu'on s'est intéressé à TAP-PFN qui est une méthode qui est un algorithme réseau de neurones type transformer, qui a été publié cette année, donc c'est tout récent en janvier, avec une très grosse publication dans le journal Nature, et qui a montré des performances excellentes pour des tâches de prédiction, pour des jeux de données allant jusqu'à 10 000 observations et avec moins de 500 variables. Et tout ça sans avoir besoin de passer par cette étape d'optimisation d'hyperparamètres, ce qui peut amener à une réduction du temps de calcul. Et donc, TAPFN, il arrive à faire ça puisqu'il a été pré-entraîné sur des millions de jeux de données. Et donc, lorsque on va l'utiliser, on va pas faire un vrai entraînement de notre jeu de données, mais on va plutôt utiliser ce qu'on appelle Lean Context Learning, c'est-à-dire que notre jeu de données, il correspond à un prompt, comme on le connaît pour les LLM, ChatGPT, où à chaque fois qu'on donne un prompt et on fait des associations entre des mots, ici, il va être capable de sortir des résultats et des réponses uniquement en se basant avec notre contexte et son entraînement préalable, mais sans avoir besoin d'être entraîné pour cette tâche en spécifique. Ce qui veut dire que les poids de modèle ne sont pas changés lors de notre utilisation. Donc ta PFN, il va agir d'une façon similaire avec notre jeu de données ici simplifié en forme tabulaire. Et donc, on va lui dire quelles sont les variables qui vont être utilisées pour faire des prédictions et il va être ensuite capable de comprendre des relations au sein de chaque variable, mais aussi au sein de chaque observation pour nous donner la meilleure prédiction possible. Aussi, on a vu dans cet article que si on compare TAPFN et sa capacité prédictive par rapport à des fonctions qu'on connaît, on voit que quand on lui donne des points issus des fonctions différentes, il arrive à prédire très très bien ces différentes fonctions avec des formes très diverses alors que nous, on est plutôt habitué à faire ce choix méthodologique par rapport aux fonctions qu'on s'attend à voir. Et donc, ici, je vous ai mis l'exemple d'une régression linéaire où il va ne sortir que toujours des droites. Et donc, pour la plupart de ces fonctions, il sera pas le meilleur modèle pour faire des prédictions. Donc, l'objectif de notre étude a été de comparer les performances TAP-FN pour estimer l'effet moyen de traitement, donc l'ATE, avec la G-computation et l'IPTW dans un cadre causal simple, donc tout similaire au premier graphe que je vous ai montré, où on a le X, donc un traitement binaire, l'outcome Y aussi binaire, et on a aussi un set de variables Z qui, elles, vont être toutes binaires aussi. Et on a évalué, on a estimé l'ATE dans l'échelle de la différence dans notre étude. Donc, pour répondre à notre question, on a utilisé deux populations issues des jeux de données de libre accès. Donc, la première, endométacine, où on voit qu'il y a quatre covariables euh, avec 14 combinaisons uniques de ces covariables, alors que pour Rotterdam, on a, on a deux fois plus de covariables présentes, mais avec 98 combinaisons uniques de ces covariables. Ensuite, on a vérifié et on a nettoyé ces populations pour être sûr de respecter l'hypothèse de positivité. Donc, c'est-à-dire que dans toutes ces combinaisons de covariables, les deux groupes de traitement sont représentés. Et ensuite, on a respecté l'hypothèse d'échangeabilité conditionnelle par notre méthode simulation qui a été faite avec une randomisation conditionnelle. Donc, je vais vous expliquer pourquoi on a commencé par tirer dans nos échantillons simulés la variable z, puisqu'elle elle précède x et y. Et donc, on a commencé par z. Ensuite, on a tiré le traitement qui précède y. Et finalement, on a tiré notre variable outcome. Donc, ces probabilités, donc la probabilité de z utilisée pour tirer les variables z dans nos simulations, a été fait à partir de la probabilité empirique calculée dans nos populations. Et ensuite, on a tiré la variable x pour chaque observation à partir de la probabilité conditionnelle de x sachant z. Donc, cette probabilité, elle aussi, calculée à partir de nos populations. Et donc, quand on a tiré x, on a pris en compte les valeurs obtenues pour chaque observation pour z. Et ensuite, on a tiré la variable y, donc l'outcome, à partir de la probabilité conditionnelle d'y sachant x et z. Donc, pareil, aussi calculé à partir de la population. Et donc, en prenant en compte les résultats déjà obtenus dans les étapes précédentes. On a fait 1000 simulations avec trois tailles d'échantillons différents. Pour comparer TAP-FN, on a choisi la régression logistique sans terme d'interaction et XGBoost, donc s'agissant d'une méthode, un ensemble d'arbres qui performait assez bien jusqu'à l'apparition de TAP-FN pour des données tabulaires, pour des tâches de prédiction. Euh, on a évalué la performance à partir de l'estimation de l'ATE et le calcul d'intervalle de confiance à 95% par une méthode de bootstrap. Et on a suivi les deux stratégies d'inférence causale, donc la G-computation et l'IPTW, pour tous les modèles testés. Donc, je vais commencer par les résultats de la couverture d'intervalle de confiance. Donc, au niveau de la première ligne, on a les résultats pour les scénarios d'endométacine et la deuxième ligne, le scénario de Rotterdam. Dans l'axe des X, on voit les différentes tailles d'échantillons, donc 200, 500 et 1000 pour toutes les métriques testées. Et après, on a les couleurs pour les modèles et la stratégie avec les formes. Donc, la première colonne fait référence à la couverture de l'intervalle de confiance à 95%, c'est-à-dire qu'on a regardé combien de fois la vraie valeur de l'ATE tombe dans l'intervalle de confiance calculé en moyenne et on s'attend à avoir une couverture de 95%, donc il s'agit de taux nominal, et on voit que toutes les méthodes qui ne sont pas rouges atteignent ce niveau, alors que les méthodes en rouge, celles de ta PFN, sont bien en dessous de ce niveau, de ce taux nominal de couverture, notamment pour l'IPTW avec ta PFN qui diminue avec l'augmentation de la taille d'échantillon. Quand on essaye d'éliminer les biais, c'est-à-dire qu'au lieu de comparer avec la vraie valeur d'ATE, on va prendre en compte l'estimation moyenne à travers des simulations, les estimations de l'ATE moyenne euh, par les simulations. On voit qu'on corrige euh, le taux de couverture pour la G-computation avec ta PFN, mais la couverture pour l'IPTW avec ta PFN reste toujours mauvaise. Euh, Concernant la largeur d'intervalle de confiance, on voit que les méthodes qui emploient ta PFN ont des intervalles de confiance plus serrés que toutes les autres méthodes. Donc, pour les scénarios Rotterdam, donc les résultats sont similaires. Uniquement, ça prend plus de temps à atteindre le taux nominal 95% pour la plupart des méthodes. Et ça peut être dû à une plus grande complexité de ce jeu de données, cette population. Et on voit que aussi, il y a l'IPTW avec la régression logistique qui a une moins bonne couverture par rapport au scénario précédent et donc qui diminue elle aussi avec l'augmentation de la taille d'échantillon. Alors que les méthodes qui utilisent TAPFN sont tout à fait similaires au scénario avec indométacine. Et donc, dans ce scénario, l'IPTW avec régression logistique, il est aussi corrigé par le biais, alors que l'IPTW avec TAPFN reste toujours très mauvais. Et en concernant la largeur des intervalles de confiance, les méthodes TAPFN restent toujours parmi les méthodes avec des intervalles le plus serrés, alors que ici, l'IPTW avec régression logistique présente des intervalles de confiance plus larges que les autres méthodes. Donc, en lien avec les résultats précédents, ici, on présente au niveau des colonnes l'erreur moyenne et l'erreur quadratique moyenne. Et ça nous explique aussi, donc on voit que toutes les méthodes dans le premier scénario ont des résultats similaires, sauf l'AG computation avec ta PFN, ce qui explique en partie pourquoi lorsqu'on corrige des taux de couverture avec l'erreur, on arrive à atteindre le niveau attendu pour l'AG computation, alors que pour l'IPTW, ça a très peu changé puisqu'il n'est pas très biaisé dans ses estimations. Et donc, on n'a pas corrigé la taux de couverture avec ce biais. Et concernant l'erreur quadratique moyenne, elles sont toutes très similaires, à part l'RG computation, qui a des résultats un peu plus élevés que les autres méthodes. Et en bas, pour le Rotterdam, les résultats sont similaires, mais la régression logistique avec IPTW euh, a donc une erreur qui est plus loin de zéro par rapport aux autres méthodes, et la G-computation avec TAPFN qui reste elle aussi un peu biaisée. L'erreur quadratique moyenne, elle est le plus importante ici pour l'IPTW avec régression logistique. Donc, comme vous vous souvenez, au début, on parlait de temps de calcul. Est-ce que ça peut simplifier nos démarches? Et donc, on a pris aussi ces mesures et on a pu constater que on a pris presque 60 heures pour le jeu de données le plus complexe avec plus d'observations, pour tourner une estimation ponctuelle avec un intervalle de confiance avec 199 itérations avec des CPU, sachant que ce temps de calcul, il peut être très réduit si on a accès à des cartes graphiques donc à notre disposition. Sachant que pour toutes les autres méthodes, le temps de calcul, il a été enfin, légèrement supérieur à une minute. Et donc, quand on compare 60 heures à une minute, enfin, c'est très significatif dans la pratique de tous les jours. Donc, pour conclure, notre étude a plusieurs limites, notamment le fait qu'on utilise que des variables binaires euh, mais avec la possibilité d'avoir plein d'interactions et avec plusieurs combinaisons uniques. Donc, l'utilisation des variables binaires euh, n'est pas synonyme d'une pauvreté de nos populations. Et donc, l'utilisation de ces variables binaires nous permet de vérifier la positivité dans notre population. Et on n'a que deux scénarios mais qui sont eux aussi avec des résultats similaires concernant ta PFN. Notre étude a aussi plusieurs forces, notamment notre design de simulation qui reproduit les relations entre des variables issues des jeux enfin, des données de vie réelle et l'intérêt qu'on porte pour la couverture des intervalles de confiance. Euh, et donc, pour conclure, la performance prédictive TAPFN n'est pas forcément synonyme d'une estimation valide en l'inférence causale. Et cela pourrait être dû à une mauvaise spécification de modèle notamment par l'influence de prior de TAP-FN, donc c'est-à-dire tous les jeux de données qui ont été utilisés lors de pré-entraînement, et donc qui pourraient avoir un impact dans nos estimations. Et merci.
Merci Francisco. Donc il y a une remarque et une question dans le chat. La question c'est de Pierre-Yves, est-ce que c'est biaisé dans l'estimation de l'effet ou est-ce que c'est seulement la variance qui est trop faible?
J'arrive pas. Est-ce que c'est
Est-ce que c'est biaisé
la
dans
variance qui est
l'estimation de
faible?
l'effet pour TAP-PFN ou est-ce que c'est seulement la variance qui est trop faible?
Euh, donc, donc c'est ça, les résultats ils sont différents. Pour l'IPTW, donc l'estimation elle n'est pas biaisée, ou très peu. Elle est notamment moins biaisée que d'autres méthodes. Euh, pour, et donc, on peut penser que c'est un problème au niveau des poids calculés avec cette méthode. C'est notamment, enfin, on n'a pas, on cherche encore des pistes pour expliquer les mauvais résultats avec l'IPTW, euh, mais donc notamment le fait que la régression logistique, elle aussi, donc dans le scénario de Rotterdam, qui a cette tendance aussi à avoir une mauvaise couverture plus importante avec l'augmentation de la taille d'échantillon qui était uniquement observé pour l'IPTW avec TAP-FN. Mais donc, on cherche encore des pistes, on ne sait pas. Euh,
Si je peux intervenir, les poids ne sont pas stabilisés.
non.
Peut-être qu'il faudrait regarder de ce côté-là parce que la stabilisation des poids, a priori, ça va augmenter un peu la variance.
Mhm.
Et donc, ça peut peut-être redresser les choses. En tout cas, c'est connu que stabiliser les poids, ça diminue l'erreur de type 1. Donc, peut-être que ça peut être une explication de ce type de résultat. Voilà.
Mhm.
Pardon.
Oui, bah oui. Après, enfin pour les autres méthodes, on a employé exactement la même chose en variant uniquement le modèle. Mais effectivement, peut-être en stabilisant les résultats, même pour la régression logistique, ça va améliorer les résultats. Mais voilà, à tester. Pour la G-computation, en effet, elle est biaisée. Et c'est pour ça que le taux de couverture, on arrive à atteindre le taux nominal quand on corrige pour ce biais-là. Euh, voilà.
D'accord. Le commentaire, c'est Federico Baldo. Est-ce que vous avez regardé d'où PFN? Il y a une publication sur Archive.
Ouais. Oui, on n'a pas testé encore. On sait, il y a déjà au moins deux méthodes qui se disent utiles pour faire l'inférence causale, l'estimation d'effets causaux avec des PFN. Donc, il y a de PFN et causal PFN. On les a pas testés. Euh, En fait, enfin voilà, à tester, mais on pense qu'on peut avoir les mêmes problèmes parce qu'elles ne sont pas développées pour avoir des estimations d'incertitude avec des intervalles de confiance, ce qui reste une limite. Donc, il faut étudier ces deux méthodes parce qu'elles sont différentes et elles prennent en compte différemment les plusieurs types de variables. Mais oui.
Merci. Est-ce qu'il y a d'autres questions sur le chat? Et donc, est-ce qu'on peut imaginer l'utilisation justement de méthodes doublement robustes, c'est-à-dire la combinaison de la G-computation et de l'IPTW avec TAP-PFN?
Euh, donc, c'est une vraie question, on n'a pas testé, mais parce que comme elles sont toutes les deux mauvaises, enfin, elles ont une mauvaise spécification, on s'attend que cette méthode doublement robuste, elle sera aussi mal spécifiée. C'est pour ça qu'on l'a pas testé, on n'est pas allé chercher tester, sachant qu'aucune de ces deux arrivait à bien avoir des bons résultats. Euh,
Ok, merci beaucoup Francisco. Ben, je pense que s'il n'y a pas d'autres questions, we move to the last presentation.
merci.
Merci.
Ah,
From Federico Baldo, the CFOT team, about retrieving classes of causal orders with inconsistent knowledge basis.
Yes. Can you hear me all right? Can you hear me?
Yeah, it's
Okay,
good.
good.
You
Can you
you
see my
can
screen?
Yes, yes, it's okay.
Okay. Sorry if I'm switching back to English. I'm not yet ready to give presentations in French. So this has been part of my first year postdoc, is work in which basically we try to use large language models, for instance, ChatGPT, to find causal structure and then estimate causal effects from these structures. So I can move. Okay. So I'm going to be very quickly and give a super brief introduction on causal inference, also because Francisco just talked about it. Then move to applications of large language models, specifically in causal discovery, and then present the main contribution and some experimental results. So probably most of you know, causal inference deals with estimation of intervention and treatment effects. And usually we have randomized controlled trials that allow us to have a control group, a treated group, and estimate an effect on an outcome. But usually these randomized controlled trials, not usually, but they can be unfeasible or unethical. Let's think about forcing pregnant women to smoke just to see if the fetus is going to be healthy or not. And so usually what happens is that we have a causal graph, which encodes basically our assumptions on the causal relationship among variables, and we can identify confounders and then estimate the treatment effect. And usually what happens is that the causal graph is provided by an expert, but even in this case, sometimes even experts cannot draw the causal graph. And so there's a branch of causal inference that deals specifically with finding causal graphs out of data, and this is called causal discovery. So we have observational data, numerical data, and we can find a causal graph. There are many methods, but the bottom line is that these methods often rely on different assumptions, and these assumptions are often really strong, and they render these methods not really applicable in real world scenarios. So maybe we don't want to have hidden confounders. We need a lot of data to have good approximations, or we have to assume linearity. Just to give you an overview, usually a full pipeline would look like this. We have data, causal discovery, we get the causal graph if an expert cannot provide it to us. And then we have, again, data, and based on the causal graph, we can have basically a formula that estimates the average treatment effect. What we try to do here is basically switch the type of data that we use at the causal discovery level. And we basically decided to rely on textual information, which is basically provided usually by experts, and that can be used alongside large language models to identify causal structures. So there's a big trend of applications of large language models right now. This kind of craze about large language models spilled over to causal inference. And so there are many applications of large language models in causal discovery specifically. And basically the main question here is, if I have a set of variables that are described by a text, and these texts are just description that an expert would provide, can we identify a direct cyclic graph, which is a causal graph that has no cycles, so I cannot start from one node and find a path that goes back to the same node, based on the knowledge that is provided by a large language model that is encoded within the large language model. And so usually in this context, the outlook that we have on large language model is the one of an expert, which is rather imperfect actually, because as we know, large language models can hallucinate, can make mistakes, and so on. So there have been many works that I was saying before, but one of the foundational one is the one that you can see here. And so they see that they can reach really high levels of accuracy on pairwise causal relationship, identifying them, but they also identify the main issues with large language models when it comes to causal inference. So again, they can be unpredictable, they can make mistakes, but more importantly, they have a hard time distinguishing between direct and indirect causal relationship, which is crucial to identify causal graphs. So usually what happens when we have errors is that we find some measure of uncertainty over the answer that the large language model provides. One of the most famous and that we are actually used is self-consistency, which is actually used even in studies with multiple experts with contradictory opinions. And basically, you ask the LLM multiple times the same question and see if in time the answer is consistent. But the big issue here is that if you cannot distinguish between direct and indirect causal relationship, identifying a causal graph becomes basically impossible. But if we look at the way we convey in causal information, let's say in natural language, we never actually specify all the causal mechanism in a specific, relative to a specific phenomenon. Let's say, for example, the very well-known fact that sedentary lifestyle causes type 2 diabetes. Most of you understand what I'm saying, but I'm actually omitting many details in this causal relationship. So for instance, we know that this effect is fully mediated by obesity. So large language models being trained on natural language, they actually inherit this kind of behavior, which is not necessarily bad, because actually what happens here is that you're preserving the causal order. So nothing that is, let's say, an upstream cause is after its effect. And so we argue that, and we are not the first to do so, there's this work that actually started this trend, that finding causal orders for large language models is much, much easier. And so starting from this idea, we actually developed our method. So we actually have a slightly different outlook on large language models. Instead of thinking about them as experts, we think about them as knowledge bases. So basically, they encode a bunch of scientific knowledge, for instance, and we can easily access this knowledge with a prompt. So we actually think about it as not capable of reasoning, but just being capable of retrieving very quickly knowledge that comes from really vast literature. But again, since they can make mistakes, this knowledge base, we deem it to be inconsistent. And as you might guess, actually, the way we measure the reliability of the answers provided by large language models is indeed self-consistency. So basically what we do, we have a query, and we ask multiple times basically the same query, rephrasing it, but keeping the semantics of the question basically the same. So just to show you what we do, we ask the large language model itself to provide us with a certain number of rephrasing of a key question that is supposed to convey the causality, let's say. So for instance, we have two variables. Does this variable cause this other variable? Please provide us a certain amount of rephrasings, and these rephrasings must be semantic equivalent, but can have different syntaxes, basically. And then we proceed to ask directly the LLM yes or no questions based on the rephrasings. And we see how many times we get a positive response, basically a yes answer. And we average on that, and we have basically a weight or an uncertainty on a specific causal link. We can do that for all the variables involved pairwise in our, let's say, experiment. So what we would get out is a consistency metric that encodes all this consistency based on the knowledge of the large language model. And this is crucial to identify a maximally consistent graph. It's very easy. Basically, we go look at all pairwise consistency. We take the one that are higher and we orient an edge in the graph. And if we have equal consistencies, and this might happen, we actually add just an undirected edge. So we have this mixed graph with directed and undirected edges, which is not a causal graph, but just maximally encodes the knowledge on which the large language model is more certain. We can actually use this method to obtain causal abstraction that allow us to estimate causal effects. And this causal abstraction is called maximally oriented partially directed acyclic graph, mouthful that I'm going to call MPDAX. Basically, we transport the maximally consistent graph, and we obtain this MPDAX that allow us to estimate causal effect, even if we have some undirected edges. I'm not going to go into a lot of details here. Just the idea is that we need to render our maximally consistent graph acyclic. So for instance, here we have a cycle here. We remove it, we undirect it. And then based on a set of rules that come from causality, again, I'm not going to go into details, we can maximally render this graph. And then this graph is dense. So there's an edge between every pair of variables. These actually allow us to determine identifiability much more easily. So what happens is that if we have an undirected edge that is associated to the treatment variable, then the causal effect of that variable on the outcome is not identified. Just to show you a very simple example, in this case, we have the NP-DAG obtained for the maximally consistent graph. We can estimate the effect of X on Y, but we cannot estimate the effect of W on Y. And here it's fairly trivial because we have an undirected edge between the treatment variable and the outcome. But if you think about much more complex cases, we just need to see if there is an undirected edge associated with the treatment, and we know already that the total effect, the causal effect, is not identified. So just to reorient ourselves, we got the consistency matrix, we get the maximally consistent graph, we compute the NP-DAG, and then we see if the causal effect is identifiable or not. If it's not, we can actually still do something. So basically, we can recover all maximally consistent causal orders that can be derived from the maximally consistent graph. And this is one of the key contributions of our methodology. Basically, we transform the maximally consistent graph, which can contain cycles, which can contain undirected edges, to be fully oriented. So just to give you an example, again, we are going back to the maximally consistent graph, and we find, based on a method that I'm not going to explain in detail here, a version of this graph that is fully oriented, acyclic, and maximizes consistency. And this graph, being fully connected and directed, encodes a unique causal order, which is this one in this case. Additionally, we might have that there are multiple causal orders that are maximally consistent and compatible with the maximally consistent graph. And in this case, we have actually two, and they encode two different causal orders. So you might ask, what can I do with causal orders? Can I estimate causal effects? The answer is clearly yes. And it's actually fairly simple. Basically, we have to assume that there are no hidden confounders, but we can estimate the effect, for instance, in this case of X on Y, if we adjust for all the parents in this graph of the treatment variable, which in this case just amount to Z. If we look at the order, this means that we just need to look at all the predecessor of the treatment variable and adjust on them to obtain the causal effect. This is a very simple identifiability criteria. Okay, that being said, since we can get multiple causal orders, we are going to have an estimation for every order since the adjustment set might change. But actually what happens more practically is that sometimes the adjustment set can be the same and can be shared among different orders. So for instance, here we have three orders. We want to estimate the effect of X on Y, and we see that in two cases, the adjustment set is composed of the same variables. And this allows us actually to have a way more efficient computation because every time the adjustment set is the same for a set of orders, we're going to have that the causal effect is basically the same. So we just need to compute it once. Okay, so going to experimental results, we tested this method on fairly small graphs, I would say, 11 graphs actually going from 3 variables to 8 variables. We have some results on larger graphs going up to 20, but actually they're not here. We're still kind of working that up. Some of these graphs are standard graphs, but many of them actually we source from scientific literature, specifically in epidemiology and public health, just to have some realistic benchmarks. And then we compare to, let's say, two methods that are more classical, that are based on observational data, and they are trained on synthetic data. And another one that is based on textual information that is actually recovering causal orders. So to estimate the error on the recovered order, what we do, basically, we use this metric that is called deta, that just counts the number of times the order is broken. So we have that a predecessor is sorted out after a successor. And okay, so the results. So as you can see, so very important, the DTOP metric, the lower the better. We start from there. You can see that there are two methods in which we have variances. And these methods, instead of returning just one order, they return a set or a class of orders. And so when you see 0.0 in terms of variance, it means that either we got just one order and it's correct, or we got a set of orders that are all correct, basically. And yeah, so as you can see, basically METS, which is our method, is outperforming most of the others in basically the majority of the benchmarks. We have just 3 instances in which we are not the best performing, and even in those cases, we are fairly close to the best performing one. So this is fairly encouraging, and again, reiterates the fact large language model seems to be prone to learn orders. But then we also want to see what the error associated to causal effect estimation. So we determine treatment and target based on the literature, and then we find adjustment set based on the criterion that I showed before, and then we measure just the absolute error given the ground truth causal effect. So as you can see, we have the MP-DAG column, which sometimes has dashes. In this case, it means that the causal effect is not identifiable. And we have the causal orders columns that has variances, since we might get a class of orders. And just for reference, I put the error associated to our method so we can see how the error associated to causal effect estimation changes when the approximation of the order is not that accurate. So in most of the cases, you can see that the error is fairly low, even in specifically one case in which we have that we do not recover the perfect order, but we still get a fairly small error. But also you can see that when the error on the estimated order is higher, we get a higher error associated to the causal effect estimation. So that being said, this method is not supposed to find like correct causal graph. We find estimation of causal orders, and even in this case, we actually are trying to use this method to identify something that can be refined, for instance, by causal experts. Especially because this method has a lot of limitations, which are mainly associated to computational time. So when we query the large language model, we have a quadratic complexity, meaning that we have n per n, where n is the number of variables, questions to the large language model, which can be very time-consuming for larger graphs. And also the method that transforms the maximally consistent graph to the set of maximally consistent causal orders is MPR, meaning that is exponential in the number of variables and can grow very fast. So we can actually make the querying part more efficient, parallelizing the question, the prompting to the large language model. One other thing that we are actually looking into is to apply chain of thought large language models, which are actually better at reasoning, to see if they improve performances. And last but not least, there are methods that actually allow us to ground the answers from the large language model into a set of documents that can be specified by a user. So if an expert wants to use this method, they can just pick a bunch of paper that are relevant to the domain in which this method is going to be applied, ground the answer of the LLM on these documents, and use our method on top of it. And this would most likely increase performances. So that being said, I'm done. If you have any questions, I'm here.
Thank you, Federico. A very nice talk. Not sure that I have understood everything, but it was quite good. And before there's no question yet in the chat. I was wondering if you try to, of course, you applied the method to different graphs which were already predetermined, but did you try to apply the method to a data set without any graph built?
No, we haven't, because we would need to have some sort of description of the variables. And like one thing that comes to mind when you ask me this question is, you are the experts to me because I'm a computer scientist. I might come to you, you give me a description of a set of variables, that you independently draw your causal graph, and then we can compare what my algorithm provides and what you draw in terms of causal graph, and see if there are incompatibilities or something that we can add to the causal order that is found by our model, or vice versa. but it becomes very hard to apply this method, validate this method, I would say, without having a causal graph that
Okay.
kind of tells you if this is correct or not. This is one of the big issues of causal discovery.
It could be interesting to do the
Yeah,
exercise
definitely.
on a real example, a real situation. So there is a question by Pierre-Yves. Is there a way to use the LLM to actually weight the different graphs left unordered?
Uh, so if I understand it correctly, the question is, can we kind of order the graphs based on the large language model,
Yeah,
like possible graphs?
yes, using weighting.
So I'm not sure. I don't think there are other methods that actually do this. But what we can do here, if you remember this slide, but there's no guarantee here. If you have a lot of orders and you see that the adjustment set is the same for a lot of orders, you have like implicitly a sort of histograms of the adjustment sets. And you can have that some adjustment sets are way more frequent than others. And this kind of implicitly would give you kind of a weighting on which is the most common adjustment set, but you have no guarantee that actually that adjustment set is associated to correct causal orders.
Yes, there is a follow-up comment from Pierre-Yves. I think this is exactly what you said. I read it. That is your order pairs, but once pairs are ordered, maybe it would be possible for the LLM to actually provide a measure of plausibility. And I think it is what you said, what you suggested.
Mm. Yeah, I might read the question myself.
Yes, because my English accent is very good.
No, no, that's not it. I really
Uh, and there was also a question from Dacha. Did you use expert knowledge for causal discovery in your experiments?
no, like prior knowledge,
Hmm.
no. This is definitely compatible with the method. So if we know that um, a specific causal relationship is 100% sure there because an expert is telling us that causal relationship exists, we can manipulate the consistency matrix in order to make sure that every time that edge is going to be there, it's going to be correctly oriented. And yeah, that is definitely something that you can.
Okay.
Okay.
Any other question? So thank you very much, Federico.
Thank you.
And le séminaire est maintenant terminé. Notre prochain rendez-vous, c'est le 10 décembre, avec la présentation de 4 autres équipes. Et je vous souhaite une bonne fin de journée à tous et à toutes. Vous pourrez retrouver ces présentations sur le site de la faculté, le site YouTube. À bientôt. Bonne fin de journée.